that Fusion Compiler DFT can perform on the design. You'll perform a test-ready compile on the design, and then compare the types of design rule checking violations that are checked before and after DFT insertion. Let's start with design rule checking. DFT-DRC uses a shared unified DRC engine that is common between TestMax ATPG and Fusion Compiler DFT. The benefit of this way is the same design rule checker is used from before DFT to post DFT through to ATPG. It checks for the same design rule violations between DFT and ATPG tools. It shares the same design rule violation messages between DFT and ATPG tools. It also provides you with debugging via the Fusion Compiler GUI. Here's how to run test design rule checking in Fusion Compiler. Once the test protocol is available, execute the DFT-DRC command to run DFT-DRC checks. One option that is available is the -verbose option, which gives you verbose reporting. This lists details for every violation in the design, which could result in a very large log file because it will list all the sequential cells in the design. This may not necessarily facilitate a better debug. The recommendation is to use Fusion Compiler GUI to debug these violations. However, for some use cases, the user may like to look at all the violations and then fix them all at once. The default report would look something like this. It will give you the first instance of the violation, and then it will inform you how many other cells that have the same violation. In the verbose report, every register that has the same violation will be listed one by one. There are two types of test design rule checking runs that can be performed using the DFT-DRC command. Prior to scan insertion, the pre-DFT-DRC is run to determine which scannable elements can be put onto scan chains. After scan insertion, you can use the post-DFT-DRC to validate that the implemented scan chains can be traced. This is somewhat of an optional post-insertion sanity check. It also can provide you with an ATPG coverage estimate. Note that pre-DFT and post-DFT-DRC check in Fusion Compiler must be run on a gate level or mapped design. To reiterate, DFT-DRC checks within Fusion Compiler must be run on a mapped netlist. However, for certain users who want to perform some test route checking before the design is mapped, you can use the tool TestMax Advisor. TestMax Advisor tool has many other useful features beyond just checking for DFT-DRC violations. The key features of TestMax Advisor are as follows. Not only it will perform the DFT violation checks similar to what DFT-DRC command in Fusion Compiler does, it can also provide you with an ATPG coverage estimation by looking at the RTL to see if it achieves your coverage goals. It is also capable of finding hard-to-test areas to reduce patterns and test costs by selecting test points. It can also do connectivity validation based on the rules that you have provided. TestMax Advisor also has a schematic that lets you debug DRC violations at RTL. The coverage analysis report from TestMax Advisor gives you a list of rules and coverage and any action that is required to improve it. The TestMax Advisor fault browser also gives you a breakdown of the test coverage and fault coverage by hierarchy of the design. Next, let us look at the test-ready compile in Fusion Compiler. What is test-ready compile? By default, compile Fusion to initial map step synthesizes all registers out of the scan flops instead of regular flip-flops. This is similar to the compile ultra-scan option in DCNXT. The benefit of doing it this way is such that the scan flop area, timing, and output loading are taken into account during synthesis. For all the scan registers that have been mapped in the design, the scan enable input pin as well as scan in input pin are grounded. Let's talk a bit about scan style in Fusion Compiler. The scan style tells Fusion Compiler DFT what type of scan equivalent flip-flop to use during the initial test-ready compile. The proper scan style must be established prior to performing a test-ready compile. And the style must be supported by the vendor library that you have chosen. For Fusion Compiler DFT, only multiplex flip-flop scan style is supported. One feature of Compile Fusion to initial map is the ability to automatically identify shift register segments. The tool will find existing functional shift registers in the design and only replace the first register in this shift register segment with the scan equivalent. The remaining cells of this shift register segment will stay as non-scan. This will help improve timing and area quality results as we're only replacing one register as scan in a long string of shift register. The automatic shift register identification feature is enabled by default. To verify that this feature is enabled, in the log file, look for the SQM-2005 information message, which will tell you the length of the shift register that the tool has identified. If for some reason you wish to disable this optimization, set the app option to false. Next, we're going to talk about test design rule checking before scan insertion, or pre-DFT-DRC. Pre-DFT-DRC will only allow risk-free cells to be included on the scan chains. When the scan shift is risk-free, ATPG would allow scan flops on the scan chain to be considered as virtual primary inputs and outputs. In order to achieve risk-free scan, design rule checking will need to identify logics such as uncontrolled clock or reset, no clock pulse at the scan flop due to the gating of the clock, or your clock signal has been divided down, or perhaps there are unexpected asynchronous set or resets asserted at the flops, as well as hold time problems due to a short net or clock skew. All these scenarios would affect risk-free scan. So a DFT rule of thumb is the tester must fully control the clock and asynchronous set and reset lines reaching all the scan path flip-flops. Here's an example of a clock divider violation. The external clock from a tester gets divided by a clock divider, which could potentially end up with missing pulses by the time it reaches the registers as compared to the actual clock being fed in from outside the design. All of these flip-flops will be excluded from any scan path. So the solution to this situation could be to insert a multiplexer that bypasses the divider such that the external clock can now reach every register in the design, gated by a signal called async_test. With this modification, all the registers downstream can now be included in the scan chain. Here's an example log file for DFT DRC that is run before scan insertion. You can see from the message that it is running pre-DFT DRC. The focus is on scan compliance. A scan compliant flip-flop is one that would function correctly during scan shift without risk. Here's another example of a DRC violation. The registers F0 and F1 are driven by a gated clock and being controlled by the enable signals. The clock pulses can be inhibited from reaching the register F0. This could occur when any of these enable signals are asserted to 0. When this happens, registers F0 and F1 are excluded from any scan path. The solution to the gated clock test design rule checking is to use an integrated clock gating cell with an additional test enable pin that is connected to a scan enable signal at the top level. During scan shift, the scan enable signal is asserted to 1. This causes the clock gating cell to be transparent, and the clock pulses will always reach flip-flops F0 and F1. Therefore, flip-flops F0 and F1 can now be included on the scan path. The connection of the clock gating control signal will be made by insert DFT. Fusion Compiler DFT can connect clock gating control signals to any unconnected clock gating cells that it recognizes. The main goal is to ensure that the clock signal can pass through the clock gate cells during test. By default, the same scan enable signal will be used for both scan and clock gating connections. However, you can optionally define a separate scan enable signal that should be used to connect to clock gating control pins. Use the set DFT signal -type scan enable -usage clock gating to specify the signal that you would like to use to connect clock gating cells. After the initial compile step, the test enable pin of clock gating cells are tied to the ground. At the beginning of DFT DRC, Fusion Compiler will make temporary connections from scan enable ports to the test pins of these clock gating cells. Then design rule checking will take place with these temporary connections. At the end of DFT DRC command, these temporary connections are removed. The goal is to check whether or not the registers driven by these clock gating cells are scannable or not, by checking whether these clock gating cells are transparent. During pre-DFT DRC, the tool checks for D rules. The D rules are a category of rules that are checked before scan chains are built. After DFT insertion, the post-DFT rules are checked, namely C, S, X, Z, L, R, V, and etc. The purpose of checking for DRC violations is to enable highly automated structured DFT. We need to check all designs for compliance with a standard set of rules. DRC violations can show where to insert ad hoc DFT. DRC violations can prevent scannable registers from being included onto the scan chain. Some rule violations do not impact scan insertion, but could affect test pattern generation. Here's a complete list of D rules that are checked at DFT DRC stage. Notice that the rules with the impact highlighted in red would actually prevent the registers affected from being included into scan chains. When running test design rule checking, Fusion Compiler DFT automatically translates cell function descriptions from the synthesis libraries into a Verilog library that TestMax ATPG can use for design rule checking. If the cell description in the library.db has no valid function keyword, test design rule checking will treat that cell as a black box. You can use your own simulation libraries for DFT DRC by specifying the set DFT DRC configuration-libs option and give the path to the Verilog library that you wish to use. The user-specified libraries are useful for black boxes, such as memory cells or pads, or anything that you wish to specify the Verilog structural functionality. A capability in Fusion Compiler is to print out design compiler style enhanced DFT-DRC reporting. By default, the report provides a lot of information but doesn't separate them into useful categories. To enable the design compiler style enhanced DFT-DRC reporting, set this option to enable. The new reporting would separate these violations into 3 categories: modeling and user constraints, DSC violations that would prevent scan insertion, and DSC violations that could affect ATPG coverage if you're running it in post-DFT. A summary, including the breakdown of all the sequential cells, is provided at the end of the report. Here's an example of the enhanced DFT-DRC report. Next, we'll talk about DFT-DRC after scan insertion, or post-DFT-DRC. This is an example report file from post-DFT-DRC. The keyword to look for is the word post-DFT-DRC in the report log. If any violations are found, the testmax ATPG violation code will be printed in this section, after which, once scan chains are traced, this will all be reported as part of the report. An additional rule that post-DFT-DRC will check for are capture violations. These are C rules in testmax ATPG. To understand the capture warnings, remember that the last scan in cycle is completed and the scan enable signal is deasserted. Now the entire design under test is in the known state with all the primary inputs applied. The fault effect is ready to be targeted to be clocked into a scan flop. Here's an example of risk-free capture. Just prior to capture, the scan flop F0 is loaded with bit S. The intent of capture is to clock in the current state bit Y, but the bit Y must depend only on the scan bit S and the primary inputs A and B. What causes risky capture? Some risky design practices for capture include logic that captures on both edges of the clock, or clock is used as input to the flop's logic cone, or if there are hold time issues due to unexpected clock skew. A rule of thumb is the ASIC must operate correctly in functional mode. Any false paths, multi-cycle or out-of-spec paths can cause violations during the capture cycle in test mode. Here's an example of clock as data violation. If a clock is also driving this cloud of logic, then there's no predictable way to say what F1 is captured. Does it capture the clock at 0 or is it 1? So the solution to this clock as data situation is to add a gating to the clock controlled by a test mode signal. Another option possibly is to recode your logic to delete this possibly redundant clock path. Here's an example of the enhanced DFT-DRC report when run in post-DFT. As we mentioned earlier, the enhanced DFT-DRC report separates the violations into categories and are listed in this example here. Also, optionally, post-DFT-DRC could perform a quick test coverage estimation and give you a report like this. The coverage estimate can be obtained using the DFT-DRC-coverage estimate option. When this option is enabled, the tool will run testmax ATPG to determine the coverage. Only combination of ATPG is run, so the estimated coverage will be a conservative estimate. A summary report will be provided with the results of the ATPG runs. There's no access for you to modify testmax ATPG settings when performing the coverage estimate. To summarize the module, we have discussed the types of DRC checks that Fusion Compiler DFT can perform on the design. We discussed how to perform a test-ready compile on the design, and we have compared the types of DRC violations checked.
Welcome to Module 4 of Fusion Compiler DFT Synthesis Training. This module talks about DFT-DRC debugging using the Graphic User Interface, or GUI. After completing this module, you should be able to use the Fusion Compiler Graphic User Interface, or FC GUI, to debug test design rule violations. You should be also able to name some different types of pin data used with the Fusion Compiler Violation Inspector schematic. So there are debug features enabled in the Fusion Compiler Graphic User Interface, or GUI. This debug interface lets you debug either pre-DFT insertion violations or pre-DRC, or post-insertion violations or post-DRC. What it doesn't do is it will not display any simulation models read in using the set DFT DRC configuration -libs option, or any of the test models read in during the read test model command. Now, the simulation models or test models are still being honored by the DFT DRC command when you run the test design rule check, but only the synthesis models read in and linked by Fusion Compiler are displayed in the Fusion Compiler GUI. In order to bring up the GUI debug environment, within FC shell, you can invoke the command dftdrc with the -GUI option, or if you haven't started Fusion Compiler shell yet, you can directly bring up the Fusion Compiler in the GUI mode and then run the dftdrc -GUI command. Here's an example screenshot of the Fusion Compiler GUI design rule checking or DRC message browser. So the violations will show up in this window after design rule checking is done. Within the Fusion Compiler debug graphic user interface, you can drill down to individual violations. So expand the violation category by clicking on this box. You'll see the violation categories and then expand to each of the violations, and then you can select individual violations in this middle panel, and when you click on an individual violation, the tool will bring up a description of what this violation is about, and it provides you with a link for you to click on to open the schematic. So when I click on this link to open the schematic, the tool will bring up this schematic here where the violation is taking place. You can bring up the pin data to debug the violation further. In this example, where I have a clock violation, you would select the clock off pin data from this pull-down menu. The tool will refresh the schematic and show where this violation is taking place and where is the source of it. So what is pin data? Pin data are simulation values that are annotated on the schematic view. There are several types of pin data. They're used to debug different types of design rule checking violation. The pin data is annotated onto the schematic looking something like this. An alternative way to debug test design rule checking issues is to use Testmax ATPG. The Testmax ATPG is run under the hood for design rule checking, but you can also be run explicitly to debug DRC violations graphically with its Graphic Schematic Viewer, or GSV. Testmax ATPG is set up and run apart from DFT, and it will require a Testmax ATPG license. So what you will require to debug DRC violations in Testmax ATPG is the Verilog netlist, which you can write out from Fusion Compiler using this command. You need the Verilog simulation library, which is used by ATPG, and the test protocol file written out from Fusion Compiler using the write test protocol command. You will then need a Testmax ATPG run script to run Testmax ATPG and bring up the GUI. So to compare the scripts between Fusion Compiler DFT and Testmax ATPG debugging, Fusion Compiler, you specify all the DFT signals and all that. Run create test protocol, save out the Verilog netlist and the test protocol, and take this Verilog netlist and test protocol into Testmax ATPG by reading in the Verilog netlist, the Verilog simulation libraries, load the test protocol file, and run the command run drc-prescan. To summarize, you should now be able to use Fusion Compiler Graphic User Interface to debug DFT-DRC violations. You should also be able to name several kinds of pin data used with the Fusion Compiler Violation Browser. Please proceed to Lab 4 to see the graphic debug in action. This concludes Module 4 of this training. Hello, welcome to Module 5 of Fusion Compiler DFT Synthesis Training. In this module, we're going to talk about fixing design rule checking violations. In this module, we're going to talk about several available methods for fixing common design rule checking issues in the design, state the DFT requirements for asynchronous set or reset signals, and the different types of test points inserted by DFT. First, we're going to talk about fixing common violations. Here are the 3 methods of correcting design rule checking violations in Fusion Compiler DFT. You could either edit your RTL code and resynthesize your design with DFT logic, or you could use user-defined test points to insert ad hoc test points, or perhaps the last resort, which is to edit your netlist with create-net and other commands, perhaps using some kind of ECO, to fix these design rule checking violations. What we recommend is to add testability to design early on, preferably in your synthesizable RTL code. Testmax Advisor is a tool that can be used to do such early analysis. When you do design rule checking fixing, you will need to use a mode signal to switch between normal operation mode and test mode. So in this diagram, we use a signal called async_test as well as SE, standing for scan enable. When your design is in normal operation, both async_test and SE signals are asserted to 0, while during test, async_test will be asserted to 1, and SE, your scan enable signal, will be asserted to either 0 or 1, depending on whether you're in capture or shift. Use the setDFT signal view exist-type constant command to define any ports that you're going to use to switch between normal operation and test. Usually, an mode signal can enable fixes of multiple common DRC violations. The signal could be an input port or an output port of an internal cell. If the same signal is also used for new mode logic during insert DFT, you will use the set DFT signal-view spec option to also define this. A common solution for fixing such uncontrolled clocks is to bypass the uncontrolled clock using a multiplexer, similar to the example diagram shown on the right. In this example, you can see a bypass multiplexer is being inserted between the clock generator and the target register. The test mode selects between functional operation and test operation, and you connect the clock generator to the input when test mode is selected to 0, and during test, the multiplexer will choose the external controllable clock to feed into the register. Next up, let's look at some uncontrollable reset situations, starting with a power on reset. In this example, we show a power on reset module on your design that sends a reset signal into the core logic. The problem with this kind of module is the reset recovery time cannot be controlled by the ATE. The solution would be to bypass such power on reset during the entire test program. So again, we use a bypass multiplexer between the power on reset module and the downstream logic. During functional operation, the multiplexer selects your power on reset, but during test, it will select a existing reset or other primary input which is controllable, such that the core logic is now controllable by the ATE. Another type of reset violations are internal resets. Let's say you have a reset synchronizer that feeds the downstream registers F2 to F4. The problem is, during scan, your reset synchronizers could be changing state and hence resetting all the downstream registers. And hence, all the affected rev flip-flops are now excluded from scan chains. To fix this, again, you could insert a bypass multiplexer between the reset synchronizers and the downstream flops. Again, use the ASIC test signal to select between functional and test mode. For the test branch, you would directly connect the reset signal into the multiplexer. An alternative to inserting a bypass multiplexer could be inserting an OR gate, like this example. You will still connect the test mode signal ASIC test as one leg of the OR gate. Now, all the registers can be now included in the scan chains. However, there will be a test coverage impact because of a stuck at one fault on the internal reset line. So a better solution is, instead of connecting the test mode leg into the OR gate, is to connect the scan enable signal to that OR gate. Not only the flip-flops can be included in the scan chains, you achieve full test coverage on the internal reset line, and the internal reset line is now controlled by the reset synchronizer during scan capture. Next, we're going to talk about inserting test points. So what are test points? Test points are points in the design where test logic is inserted to improve the testability of the design. Fusion Compiler DFT can automatically determine where to insert these test points to improve test coverage, reducing pattern counts, or blocking access, etc. You can also manually define where test points and the type of test points to be inserted. You can configure test point insertion on a per partition basis. This is an advanced feature, and we're going to talk about this in the advanced flow section. In order to insert test points automatically, a TestMax Advisor license is required. One feature that Fusion Compiler offers over other solutions is the ability to insert test points that are physically aware. So in Fusion Compiler, during test point insertion, the tool will consider both testability and design constraints at the same time. TestMax Advisor is used to analyze the locations where test points are needed, and within Fusion Compiler, the test point pins will share registers according to the physical proximity. Let's talk about the types of test points being inserted by Fusion Compiler. First type is force test points. This allows a signal to be overridden throughout the entire test program and typically is used to block values from propagating, such as X's. Another type of test points is control test points. It allows a hard-to-control signal to be controllable for some test vectors but not others. These are typically inserted to increase the fault coverage of the design. A third type of test points are observed test points. These are inserted at hard-to-observe signals to reduce test data volume or to increase the coverage. To enable or disable test point insertion in Fusion Compiler, use the command set DFT configuration -testability option. The default is disable. Select enable to enable test point insertion. Once you have enabled test point insertion, you need to use the command set testability configuration to configure how test points are being inserted. You will need to select one or more test point targets, such as random resistant, untestable logic test points, or perhaps user-defined test points. You can configure test points on a per-target basis. If you need to customize test points analysis, you can use a TestMax Advisor command file and pass this command file using the option -sg_command_file. Once you have configured the insertion, you will need to run the command run test point analysis after pre-DFT design rule checking to enable TestMax Advisor to perform test point analysis. The three test point targets supported by Fusion Compiler are as follows. Random resistant test points would improve random pattern coverage. Untestable logic would make untestable logic testable. The type user lets you insert user-defined test points provided in an external test point file. You can configure global test point insertion settings by not specifying a -target option to the set testability configuration command. For instance, you can specify a global clock signal or control signal for all the test points that you want the tool to insert. For some local target-based settings, you can also configure the effort, such as random resistant test points, or you want to use a different control signal for the target random resistant, then you can specify -target -control signal in the same command. You can specify a test point target either through command or through an external file. Specifying a target through the command option enables Testmax Advisor or Fusion Compiler DFT analysis to find test points for a specific target, and it enables implementation of that set of test points. You can specify the global -test point file option. This test point file may be user-defined or provided by a Fusion Compiler DFT run. If you do it like this, the test points from this file will be added to their respective buckets only. A test point bucket is not implemented unless its target is configured. You can also specify the per target only from file true option. This way, you will suppress Testmax Advisor or Fusion Compiler DFT analysis for that particular target. It will implement that target's bucket as populated from that file. Note that the -only from file option is only meaningful when you supply the -test point file option. Let's say you have an external file containing random resistant and untestable logic test points that you would like to insert. You first pass the file name of this test point file using the set testability configuration -test point file option, as well as enable insertion of random resistant and untestable logic test points. When you do the run test point analysis command, Testmax Advisor will analyze the design as well as take the test points that you have specified into the command into account. The analysis by Testmax Advisor may result in additional test points that will be inserted by insert DFT command. However, if you specify the name of an external file as well as specify the -only from file option to be true, no additional test points from the analysis by Testmax Advisor will be inserted. Here's an example test point plan report. In the test point plan report, the tool will print the names of the test point registers that it is about to insert, as well as the clock signals or control signals, as well as the type of test points that this test point register acts for the pins that is going to be inserted, as well as a test point summary showing the types of test points that the tool is about to insert. Here's an example test point insertion script for Fusion Compiler. First, enable test point insertion using the set DFT configuration -testability enable option. Then configure each of the test point targets using the set testability configuration -target option. For example, here I am targeting random resistance test points. With a clock signal, I'm specifying the maximum number of test points for this target, as well as specifying the test point enable and control signal for this target. For untestable logic, I'm specifying a different control signal, as well as a clock, which is shared for random resistant test points. After the commands create test protocol and DFT-DRC, you will need to run a command run test point analysis to perform test point analysis on the design to determine the test points that are needed to be inserted. One feature that is shared between Design Compiler Graphical as well as Fusion Compiler is the tool will use physical proximity to group the test point pins. So the example above, you can see that the test points are not grouped by its physical proximity, whereas in DC Graphical or Fusion Compiler, the test points are grouped physically nicely like this to reduce wires crisscrossing across your design. Grouping of your test points is performed independently for each combination of the test point type, test point clock, as well as the power domain. To summarize this module, we talked about the several available methods for fixing common design rule checking issues in the design. We talked about Hello, welcome to Module 6 of Fusion Compiler DFT Synthesis Training. In this module, we're going to talk about top-down scan insertion flows. So in this module, we're going to talk about inserting scan chains into a design using a top-down flow. You'll learn to specify and insert balanced top-level scan chains, reusing existing functional top-level pins for scan, as well as specifying and previewing scan chain architectures. First up, we're going to talk about specifying your scan configurations. To specify your scan architecture, you'll be using the command syscan configuration. This command is used to specify scan chain properties, such as how should the tool handle multiple clocks, the number of scan chains or the length of the scan chains, whether or not to insert lockup elements, and any registers that need to be omitted from scan chains. First up is to handle different clocks in your design. You will use the -clock mixing option to specify to the tool whether or not scan synthesis should build scan chains with different clock domains on the same chain. Mixing clock domains on the same chain would usually require lockup latches to be inserted at the domain crossings. Next up, you will use the syscan configuration -chain count option to specify the number of chain counts that insert DFT command is going to build. The default will be to build the minimum number of scan chains given the clock mixing constraints that you have specified earlier. You can use the -max length option to specify to insert DFT command to build scan chains without exceeding the specified length. The -add lockup true or false option would enable or disable insertion of lockup elements when crossing different clock domains during scan chain synthesis. Other flavors of lockup latch insertions include inserting terminal lockup true or false. When it's true, the tool will unconditionally insert lockup elements at the end of the scan chains. Also, you can specify the lockup type that is going to be inserted by the tool, whether it's going to be a latch or a flip-flop. The default is latch. Lockup elements, whether they are latches or flip-flops, are used to allow scan chains to cross clock domains. What they do is they mitigate the skew between the two clock domains to ensure that the data is shifted reliably on the scan chain. Typically, the clock driving the lockup element is the inverts from the clock that is driving from the previous flip-flop, such that the latch will hold the data from the previous flip-flop for additional half cycle. In this example, we show part of a scan path which are clocked by both edges of the same clock, and these scan cells are mixed into the same chain. During ordering of the scan cells, tool will obey what we call a nice rule, which is the next instance must be clocked concurrently or earlier in the tester cycle. So in this example, the rising edge is clocked earlier than the falling edge. Therefore, registers that are clocked earlier must follow registers that are clocked later. The same principle applies whether or not we are mixing clock edges or mixing scan clocks. Here are the rules for inserting lockup latches. When a scan path crosses clock domains, the timing of the two clocks can affect whether a lockup element is required. So let's say you have two clocks with the same set DFT signal -timing option. What this means is there is a risk of skew, and by default, a lockup latch will be inserted at the clock domain crossing to add a half cycle extra hold time. Whereas if you have clocks that are specified with different -timing option, then the tool will assume that there will be no skew in the clock, and scan flops are placed in the nice order, and we
tool will assume that the timing phase difference is greater than the worst case clock skew between the clocks, and therefore no lockup latches will be inserted. Here are the 4 scenarios for inserting lockup latches. Back-to-back positive to positive edge triggered registers, the tool will insert lockup latches. Similarly, negative to negative edge triggered back-to-back registers, the tool will insert lockup latches as well. A positive to negative edge triggered will never happen by default in Fusion Compiler, since the tool will always order later triggered registers earlier in the train. One exception could be a retiming flip-flop. For a neg-edge to pos edge triggered, the tool will not insert a lockup latch. In fact, there will be a potential hold time issue if the tool actually inserts a lockup latch. Next, let's talk about the trade-off between scan access pin and tester time. The longest scan path in your design will determine the number of vectors per pattern, and thus the tester time per pattern increases directly with the longest scan path on the design. Let's say you have 32 registers in your design. With only 3 access pins, scan in, scan out, and scan enable, the tool will build one chain of 32-bit. Therefore, for each pattern, the tool will require 32 clock cycles to shift through this whole chain. Whereas, if additional access pins are available, you can now split this one chain into 4, therefore reducing the tester time per pattern by 4. Therefore, to increase the number of test access pins, you could consider using a functional input pin as a scan in port. To do that, use the setDFT signal -type scan data in and specify a functional input port as your scan data input. You can also consider using a functional output as a scan out port. To do that, specify setDFT signal -scan data out and specify your functional output port. What the tool will do is it will add an additional multiplexer to select between the functional path and the test path. Next, we're going to talk about how to preview your scan configuration. Before actually inserting the scan chains, you could use the preview DFT command to check your scan architecture. Scan preview will give you a report of the chain count that the tool is about to insert, as well as the allocation and the order of the scan cells. The default is the minimum number of scan paths that is consistent with your clock domain, clock mixing, and rebalancing options. Whereas for allocating and ordering the scan cells, the tool will build any explicit scan path specifications first, then assign other flops to paths grouped by the common clock and then by the block. After specifying the scan architecture and your test points, you can do preview DFT to look at the scan chain architecture that the tool is about to insert. This lets you make changes to your specification if you realize that the tool was not building the scan architecture as you had expected. Once you're happy with what preview DFT command gives you, you can then do the actual insertion of the scan paths and the test points. Here's a typical preview DFT report. In this report, you can first see the number of scan chains that the tool is about to insert for each of the test modes that the tool will insert. For each of the scan chains, it will print the scan chain cells and the segments for that particular scan chain, as well as any multi-voltage information, clock domain, and timing associated with that chain. Here is another preview DFT report. In this report, we have one scan chain that consists of 2 different clocks. Here you can see the tool will print the name of the clock domain, the timing, whether they're rising and falling, as well as whether or not lockup latches are inserted between the clock transition. Next up, we're going to talk about inserting the DFT logic. You can use the setDFT insertion configuration command to specify DFT insertion parameters. The option available to you is -unscan true or false. Default is false. This lets you specify whether to unscan cells with DRC violations during DFT insertion. In Fusion Compiler, use the insert DFT command to perform DFT insertion. First up, it will insert any test points if you have enabled. Then it will assemble the scan paths by stitching the design across your access points, scan cells, scan segments, etc. It will then try to minimize the violation, optionally unscanning any excluded scan flops. Fusion Compiler DFT does not automatically create top-level scan ports that are needed to meet DFT architecture requirements. So this is a difference between Fusion Compiler and Design Compiler DFT. Preview DFT command will error out and indicate that the tool cannot build the design. If this is not expected, check your chain count or clock mixing settings. Next up, we'll talk a little bit more on controlling how scan chains are inserted. You should always aim to build as balanced a set of top-level scan chains as possible. The reason is, the number of test cycles required per scan pattern is really determined by the longest scan chain. Any unbalanced scan chains will lead to wasted test application time on your tester, wasted pattern memory on your tester, and ultimately increasing your test cost. The tool default in Fusion Compiler is to not mix clocks on a scan chain. The tool will balance the scan chain as well as possible given the mixing restriction. Any non-default clock mixing options, mix edge, mix clocks, and mixing clock not edges, could result in better balanced scan chains because now the tool will build multiple clocks in the scan chain or multiple clock edges in the single chain. By default, the tool will not mix clocks along a scan path. Therefore, the default chain count is one scan path per clock domain. If your design has many clock domains, this will impact the scan chain balancing. So, for better balancing at a lower risk, you could mix edges of the same clock by specifying dash clock mixing mix edges. You could also achieve optimal scan chain balancing with required lockup latches by specifying dash clock mixing mix clocks. In Fusion Compiler, you would declare clock signals using the setDFT signal command. This identifies the test clock domains to the tool. So in this example, we have used setDFT signal command and specified a top-level clock. Even though this signal might have gone through a multiplexer and gated with a selector signal, the tool will still consider the design has only one test clock domain. In this example, we have a clock inversion along the clock network. You will still use the setDFT signal command to define a clock at the top level. However, the preview DFT command will now see two distinct clock domains, one for each edge. By default, since no clock domain mixing is possible, Fusion Compiler DFT will insert a separate path for flip-flop F2. Let's discuss internal clock domains. By default, Fusion Compiler DFT does not consider any internal clock domains. Only top-level clocks are considered as a source of clock. However, you could use the following command, setscan configuration-internal clocks, to control whether Fusion Compiler considers internal clock domains. Default is none, which means Fusion Compiler will not consider internal clocks. If you specify multi, Insert DFT will treat internal clock network regions driven by multiple input gates, such as multiplexers, as separate clocks for the purposes of scan chain architecture. Buffers and inverters are transparent. You can also specify single, which will treat any combination of gates, such as buffers and inverters, as separate clocks for the purposes of scan chain architecture. You can specify internal clocks globally or locally. The global internal clock options will apply across the design, whereas if you use the local option, it will only apply to the fan-out of a specific scan clock. Globally, you can use the setscan configuration internal clock option. Locally, you can use the setDFT signal-internal clocks option. In this example, you can see there are 3 clock domains if you specify the -internal clocks multi option. First clock domain is the top level port. Second domain is the clock coming out from the multiplexer. The third clock domain is the signal coming after the inverter. One point to note is clock gating elements are not considered when identifying internal clock domains with the internal clock single or multi option. So in this example, the clock gating cell here does not result in an additional clock domain. You can associate an internal clock source with a top-level clock by using the -associated internal clocks option. What this does is the listed pins here in this example will be considered as internal clock sources by the tool. For example, we now have a top-level clock as well as 2 separate internal clock sources after these buffers because we have specified the -internal clock option. In some cases, you may need to give manual guidance to the tool for lockup latch insertion between parts of the design with different clock tree latencies. Scan skew group is a group of scan cells that might have a different clock latency characteristics than other parts of the design. Using the setscan skew group command, the DFT architect will treat the skew group as a unique skew subdomain. The include list can contain leaf cells, hierarchical cells, or CTL model cells. Using the setscan skew group command, preview DFT will report the scan skew group name as the clock name. Now, if scan cells from different scan clock domains are in the same scan skew group, the tool will treat all cells in the scan skew group as if they were in the same clock domain, and no lockup latches will be inserted between them. So here's a short quiz. How many scan chains would the tool insert in each of these situations? To summarize, we have discussed inserting scan chains into a design using top-down flow. We talked about specifying and inserting balanced top-level scan chains, and in particular, we talked about internal clocks, clock domains, and the effect of clock domain specification in balancing scan chains. We talked about reusing existing functional top-level pins for scan chains. We talked about specifying and previewing scan chain architectures before the actual DFT insertion.